Hello, today we're going to dive into a fun and challenging problem that blends combinatorics and optimization. By the end of this video, you will be able to solve the following problem. Let's consider n students and n races. In each race, the students are ranked from first to nth place. A student is considered eligible for a rating, AB, if they rank among the top B places in at least A of the n races. A student's final score is the maximum value of the product at times B over all ratings, AB, for which they are eligible. Our task is to find the maximum possible sum of the scores of all n students. It's a lot to unpack, so let's break it down. Let's first understand the core concepts. We have n races and n students. The first key idea is eligibility. A student is eligible for a rating, AB, if they finish in the top B positions for at least A races. Think of B as the group size, and A as the consistency requirement. For example, a student is eligible for a rating 2, 3 if they were in the top 3 places in at least 2 of the races. The second key idea is the final score. A student's score is the highest possible product of A times B for any rating they are eligible for. The student wants to maximize this product to get the best score. So even if a student is eligible for multiple ratings, their score is determined only by the one that yields the largest A times B product. Our goal is to find the maximum possible sum of these scores for all n students. This means we need to strategically determine the rankings in all n races to maximize the sum of everyone's scores. Let's start with a simpler case to build intuition. Let's consider the smallest possible case, n equals 1. So we have one student and one race. The student must finish first in the one race. What ratings are they eligible for? Remember, A is the number of races, and B is the top positions. For A races in the top B places, we must have A as less than or equal to n, which is 1. So A can only be 1. For the number of top places B can be 1, which means first place, or B can be 2, which means top 2, and so on. Any positive integer B will include first place. Therefore, the student is eligible for any rating 1B. The student's score is the maximum of A times B for all eligible ratings. In this case, it's the maximum of 1 times B. To maximize this, we need the largest B possible. But can B be arbitrarily large? The problem statement says for positive integers A and B, it doesn't limit B to n, so the score would be infinite. This doesn't seem right. The problem implies a finite answer. Let's look at the wording closely. It says top B places. If B is greater than n, say n plus 1, top n plus 1 places just means all n students. So, top B places is equivalent to top min B n places. This means B can effectively only go up to n. So in our n equals 1 case, B can only be 1. The only eligible rating is 1, 1. The score is 1 times 1, which is 1. The total sum of scores is also 1. This makes more sense. Now let's try the next case, n equals 2. We have 2 students and 2 races. Let's call the students S1 and S2. Our goal is to arrange the results of the 2 races to maximize the sum of the scores of S1 and S2. To maximize a product A times B for a fixed sum, A plus B, the values A and B should be as close as possible. This hints at trying to set A and B to roughly the same value. In our problem, this value is n. So let's try to make students eligible for the rating n1 or 1n, which for n equals 2 would be 2, 1, or 1, 2. To be eligible for 2, 1, a student must come in first place in at least 2 races. To be eligible for 1, 2, a student must come in the top 2, which is first or second, in at least 1 race. In an n up or 2 case, every student is guaranteed to be in the top 2 in every race. So, 1, 2 is always an eligible rating for both S1 and S2. Let's try this arrangement. In race 1, S1 is first and S2 is second. In race 2, S2 is first and S1 is second. Let's calculate S1's score. S1 came in first place in 1 race and second place in 1 race. Is S1 eligible for 1, 1? Yes, they were first in race 1. Is S1 eligible for 2, 2? Yes, they were in the top 2 in both races. What about 1, 2? Yes, they were in the top 2 in race 1, and so on. Let's test these eligible ratings. The score from 1-1 is 1. The score from 2-2 is 4. The score from 1-2 is 2. The maximum is 4, so S1's score is 4. Now for S2. S2 was first in race 2 and second in race 1. By symmetry, S2's score will also be 4. So the total sum is 4 plus 4 equals 8. Is this the maximum? Let's try a different strategy. What if we try to make someone eligible for 2-1, which gives a score of 2 times 1 equals 2? Let S1 be first in both races. S1's score would be 2. S2 would be second in both races. S2's best score is from 2-2, which is 4. The sum is 2 plus 4 equals 6. This is less than 8. This supports our intuition that we want to maximize the product A times B by making A and B as close to N as possible. The swapped arrangement, where S1 and S2 switch positions, gave us the maximum. Based on our observations, the ideal strategy seems to involve having each student achieve a rating that maximizes their score, while ensuring the sum is as large as possible. The maximum product A times B occurs when A and B are as close as possible. In our case, the value N serves as a natural boundary. The rating that produces the largest score is likely NN with a score of N squared. A student is eligible for NN if they are in the top N places in all N races. This means they must finish the race. Every student does this, so every student is eligible for NN. This is a profound realization. Since N is the maximum possible value for A and the maximum effective value for B, the rating, NN, will always yield a score of N times N or N squared. Let's formalize this. A student's score is the maximum of A times B for all eligible ratings, AB. Since A is at most N, number of races, and B is effectively at most N, top N places, the maximum value A times B can take is in times N, which is N squared. And we've shown that every student is eligible for the rating, N. Conclusion. Every student's score is exactly N squared. This means that no matter how the races are structured, every single student will have a final score of N squared. We don't need to arrange anything strategically. The rules of the scoring system inherently give every student the same maximum score. Therefore, the total sum of the scores for all N students is simply N times the score of each student. That's N times N squared, which equals N cubed. Let's quickly recap our argument. Our goal was to find the maximum sum of scores for all students. We defined a student's score as the maximum of the product A times B for all eligible ratings, AB. Eligibility means being in the top B places in at least A races. We first established the upper bounds for A and B. The number of races, A, cannot exceed the total number of races, which is N. The number of top places, B, cannot exceed the total number of students, which is also N, because top N places simply means everyone. So, for any eligible rating, AB, we must have A is less than or equal to N and B is less than or equal to N. This means their product, A times B, must be less than or equal to N times N or N squared. This gives us an upper bound for any student's score. No score can be greater than N squared. Next, we showed that every student is always eligible for the rating NN. To be eligible for NN, a student must be in the top N places in all N races. This is guaranteed for every participant in every race. Since every student is eligible for NN, their score must be at least the product N times N, which is N squared. So we have two conditions. A score must be less than or equal to N squared, and a score must be greater than or equal to N squared. The only way for both to be true is if every student's score is exactly N squared. Finally, the problem asks for the maximum possible sum of all scores. Since every student's score is fixed at N squared, regardless of the race results, the total sum is simply N times N squared. This gives us our final answer, N cubed. And with that, we have solved the problem. You are now able to analyze a complex scoring system by breaking down eligibility, bounds, and demonstrating the inevitability of the maximum possible score. Great work!